So in our next section, we're going to continue our example with BGP with VPLS for Autodiscovery. The difference between this example and the last one, though, is now we're going to use BGP for not only Autodiscovery, but we're also going to use it for signaling of the label value. Where in the previous case, what we had was that there were 3 provider edge routers, which were router 2, 4, and 5, and we had them configured as BGP peers of router 6, which was the L2 VPN route reflector. So then on each of the provider edge routers, we had our virtual forwarding instance configured. And under the VFI, this is where we configured the VPN identifier. The VPN identifier ultimately is what becomes our route distinguisher that's advertised as a layer 2 VPN route. So from router 6 on the route reflector, if we look at the show BGP, L2 VPN, VPLS for all route distinguishers, we see that we have a couple different types of routes. Okay, so we have one distinguisher that is 1:200. We have another one that is 1:1234. These are the VPN identifiers that we had previously configured under the VFIs. And it looks like, did this guy crash? No. Yes, this guy crashed. Okay, let me get its config back. Let's look at the show run. And it should have the, no, it doesn't have the config. Okay, let me load the config back in here real quick. So when you're practicing this on either Viral or if you have other VMs like an ESXi, you do kind of have to be patient with some of the L2 VPN features, because I think it's still kind of in its infancy of the support in virtualization. So this guy is this one, router 5. Okay, so let me restore its BGP config, which was this here. Okay, so we're peering with router 6. And if we show BGP, L2 VPN, VPLS, all summary, we should see here that we have a peering over to 6, which we do. Okay, so the next step is that we're going to reconfigure our bridge group and our VFI. And the difference is that under the VFI, we're going to say we're using BGP not only for the discovery, but we're also using it for the label signaling. Because as it stands now, when we go to router 2, for example, and look at the show MPLS LDP neighbors, we have a targeted LDP session that's going to the other provider edge routers we discovered were part of the VPLS. So BGP found the neighbor, and then LDP established the label session in order to actually advertise the VPN labels. But in this example, BGP is going to do both of those. So it's more similar to the inter-AS options that we looked at before, where we're doing BGP plus label. Same thing here, except it's a layer 2 VPN BGP plus label. Now, from a configuration point of view, it's going to be fairly similar to our last example, which was to say that we have the L2 VFI with the VPN identifier, and then we're doing BGP Autodiscovery. The difference is that this keyword here is going to change to BGP. Okay, additionally, we're going to have to configure some other options under here to advertise what label space that BGP is going to say is valid to advertise to the peers. Because we need to make sure that if you're using label 10, that someone else is not also using label 10 as the traffic comes into me, because it has to be globally unique based on the incoming label value. Okay, so let's undo essentially the config that we have on 2 and 4, because we're starting from scratch on 5 anyways. So let's say default interface gig 2 and gig 3. Let's show run, pipe to include bridge or VFI. And then let's get rid of both of these. So let's get rid of the bridge domains. And the virtual forwarding instances. Okay, same on router 4. Show run pipe to include bridge or VFI. No bridge domain 2, no VFI. Okay, so first we're going to look at the signaling of the routes. Signaling of the routes is going to be part of the virtual forwarding instance. That's where the BGP Autodiscovery config is going to be listed. Once the routes are then discovered, we will then bind the VFI to the bridge domain, which is actually going to connect it in the data plane to the local interfaces. So we're going to configure a new VFI. We'll say that this is going to be BGP signaling, okay, any locally significant name. We need to give it a VPN identifier. So we'll say 10, okay, as long as it matches between the three of them. We then want to say we're going to do auto discovery with BGP, but that the signaling protocol is also BGP. Okay, so it's kind of redundant. It's for signaling and discovery. Okay, under BGP, we then need to specify what the VPLS edge identifier is. Okay, this has to be a unique number for each of the PE values, but it's only a locally significant number within that individual route distinguisher. So theoretically, you could have up to 16,000 PEs within an individual VPLS, which is more than a realistic number. Okay, so for simplicity, I'm going to say this guy is 4, and then routers 2 and 5 will be 2 and 5 respectively. Okay, what this is also going to control is what the range of labels is that we are advertising. Okay, so this I'm going to come back to in a minute after we actually establish the BGP peers. So let's say show run section VFI, and we're basically going to say the same thing on all three of these, except the VE ID is going to be different. Okay, so on router 2, we'll say the VE ID is 2, and on 5, we'll say the VE ID is 5. Okay, next on router 6, if we look at the show debug, we're debugging L2 VPN, okay, which is debug BGP L2 VPN, or debug BGP L2 VPN, VPLS updates. Okay, from 6, if we look at the show BGP, L2 VPN, VPLS all, right now we're not learning any routes because the previous advertisements were withdrawn when I deleted the VFIs. Now, what's a little bit strange about this config is that by default, when you peer with a neighbor under L2 VPN, iOS is assuming that you want to do the signaling with LDP. And for whatever reason, LDP takes preference over BGP. What we now need to do is to say for this peer, don't use LDP for signaling, we want to use BGP for signaling. The way that we do this is when we show run section BGP, is to say the neighbor under L2 VPN, we're going to suppress the signaling protocol and we want to suppress LDP. Okay, now notice if we look on router 6, what happens when we enable that on one side versus the other is that we get a BGP notification. Notification means that the neighbors don't agree on some sort of attribute when they go to do the capabilities exchange. So basically what's happening is that router 2, in this case, I think it was, router 2 said, I want to use BGP for labeling. The route reflector is saying we're going to use LDP for labeling. Protocols are not compatible, ends up that we're going to tear down the BGP session. So we need to make sure that this agrees on all of the sides. So on router 6, if we look at the show run section BGP, what I need to change is under this layer 2 peer policy, the L2 VPN policy, we're going to say here under peer policy that we're going to suppress the LDP advertisement. Okay, so it's going to be under this top, and let me debug here. Show run section BGP is under this one. We're going to suppress signaling protocol LDP. And since I already had the template applied to all the neighbors, it means it's applying to 2, 4, and 5. Okay, the other syntax that I used on router 2, we can just basically copy and paste this to the other ones, which is that portion. So 4 and 5. Okay, on router 6, if we now look at the debug BGP, L2 VPN, VPLS updates, we should see that once the neighbors come up, we actually start to advertise what the label range is that those neighbors are going to use when they actually form the pseudo wires together. So it's this kind of strange format for the update. And I'll show you in a second where the document is that describes what does this actually mean in terms of the label numbers. Okay, if we look at the show BGP, L2 VPN, VPLS all, we see the actual routing advertisements. Now, the most important portion of this is what is the label range and then what is the next hop of the neighbor. So the first thing is that we need to figure out who are the neighbors. That's by advertising the next hop value. So we know that part of this VPLS 1:10, we're using 2222, 4444, and 5555. If we go to any of the other BGP neighbors, so the PEs, and look at the show BGP, L2 VPN, VPLS all, we likewise should be learning about those routes. Okay, if we look at the show L2 VPN VFI, this is what's going to tell us that we're going to establish pseudo wires to those particular destinations. Now, within the pseudo wire, we then go to exchange BGP in order to actually do the signaling about what label values that we're going to use. So the difference now from this previous example is that if we look at the show MPLS LDP neighbors, we're no longer going to have a targeted session between 2, 4, and 5. Instead, we're advertising the labels with BGP to the route reflector. The route reflector is passing them back on. We now discover that the other endpoints are router 4 and 5. We set up the pseudo wires, we learn the labels from them from BGP, and then ultimately we can start to forward the traffic. So from the previous example, there's really only 2 changes here. One is that we need to set the, well, actually 3 changes. One is that we need to set the signaling protocol to BGP. We need to give it a VPLS endpoint identifier that is unique. And then we need to say, don't advertise LDP as the signaling protocol between them. Okay, there's a question here, is the route reflector in the data plane? No, it's not. So this would be the same effect as if we did a full mesh of iBGP L2 VPN between them. When we actually go to look at the label forwarding, we're going to use the transport label between the PEs, which in this case was based on OSPF plus LDP. So if we look at the physical topology, this means that when we go to bridge traffic from router 1 to 7, the traffic is going to come in. Router 2 is going to say, okay, this came in on service instance that was on gig 2. Look at where the service instance is bound to the bridge domain. From the bridge domain, this is basically the CAM table. It's the MAC address table of the switch. So it says, look up the MAC address, find the MAC address of router 7. This is going to point at the pseudo wire that goes to 4. We know the pseudo wire endpoint ID. We figured that out from BGP. It's 4444. Now do a global BGP, or not a global BGP, a global routing lookup on 4444. We find the transport label switch path towards them. And in this case, we're going to go over to router 3 and then down because I have this interface disabled between them. But we don't need to label switch over to the route reflector and then come back, because the route reflector is used just to pass the updates between them. Okay, so the final portion of this would be to bind the VFI to the bridge domain in addition to the physical port. So if we show run interface gig 2, on gig 2, this is where we're going to have our service instance. Okay, we'll say service instance, whatever, 100. Under the service instance, what's the VLAN that we want to match? If we say VLAN default, that's going to be catch-all. Okay, so it's everything. And then under the bridge domain, say 300, the members are going to be gig 2 with service instance number 100. Okay, and normally you would just put these numbers all the same. I'm making them different just to show that they're not directly related to each other. But for a clarity of operations, you would use the same number over and over and over. Then we'll say that also the member is the VFI, and the VFI is BGP signaling. Member VFI, BGP sig. Okay, we should see that the VFI comes up. If we look at the show bridge domain, we should be learning about our local MAC addresses. Okay, so that's on the physical port, or more specifically, what they're calling the Ethernet flow point, which is the service instance. In this case, it was service instance number 100 on that physical interface. But if we take this same config now that we did on router 2, and basically we can just replicate it on the other side, which is bridge domain, since we use the same VFI name, and we can do the same thing on the physical interface because the naming convention is the same, we'll create the service instance. Then in global config, bind it to the bridge domain. And we should see they automatically form a full mesh of data plane connectivity. Okay, so from router 1's point of view, we should see in a second that we form adjacency with router 7 and router 8, which are down here. So if we ping to the broadcast address, we have reachability to 8, not 7 yet though. So 7 is on attached to router 4. This says service instance 1 is already configured as the default service instance. Okay, so you cannot overlap the numbers. If we look at the gig port, I just need to start that over. There's a question here, does the bridge domain need to be the same on all the PEs? No, it does not. The only thing that really matters between them is the VPN identifier, because that's what the virtual circuit identifier is for the pseudo-wire. So for the sake of argument, let's say I'm going to make it different on router 4, just to show that it can be different numbers. So we'll say that on gig 2, we're using service instance 444. That's bound to the bridge domain 555. VFI is already associated. Okay, so now I need to delete them. No bridge domain. Let's do this. Show run in VFI or bridge. No bridge domain 300. Okay, it went to up. If we look at the show L2 VPN VFI, this tells us whether the circuits are actually up. Okay, so pure addresses are 5 in router 2. If we then look at the show bridge domain, we're learning our local MAC addresses, which are on the gig port, and then we're learning the remote MAC addresses, which are on the remote pseudo wires. Okay, so basically each of the interfaces, or each of the neighbors, get a logical pseudo wire interface address. This is if you want to configure things like QoS to an individual neighbor, you can apply it under these particular ports. So if you say under the interface, manual pseudo-wire only goes up to 100,000. In this case, this is because we did auto-discovery, but if you're doing manual configuration, you can put other attributes that you want to on the pseudo-wire interfaces directly. Okay, now from the data plane point of view, again, we should see that we have a full mesh of connectivity. So if we now look at from the data plane, and if we look at traffic that is going between, let's say IP.source is equal to 2222 or, let's see if I have my syntax right here. Can I say or 4444? Or, no, I don't think I can do it that way. Let's just say 2. And let me restart the capture. What we should not see here is LDP used for signaling from router 2. Now, it will be used for signaling in the core, which in this case is between router 2 and router 3, because this is the OSPF plus LDP signaling. But then we're going to advertise with BGP over to this guy, BGP L2 VPN, that this address 2222 wants to form a VPLS, and the VPLS identifier was, if we look at the show run section VFI, identifier was number 10. So again, what this is used for is to determine the route distinguisher. We have the BGP AS number, which is 1:10. For the other neighbors that likewise match this distinguisher, it means that they're part of the same routing table for VPLS. But VPLS is not advertising the MAC addresses, it's advertising just the endpoints and then the label number that we're going to use in the data plane to transport it for the VPN label. Okay, so let's look at this now from the data plane. We go over to router 1, and we do so let's say it's IP source 2, or it is ICMP traffic. So from router 1, let's look at the show IP route, OSPF. Let's ping to 7777. Okay, if we look at this from a capture point of view, what we should see is that as it comes in from the Ingress PE, so this first ping request, it has a 2-label stack. Okay, in this case, it's number 35 and 35 on the outside, 31 on the inside. Okay, 35 on the outside, this is the one that is going to be referring to the LDP transport label. So if we go to router 2, which was the PE, and on router 2, we look at the show MPLS forwarding table, and we find number 35 outbound, it means it's going towards router 4. Okay, also notice that there are some label values that are associated to the layer 2 circuits. Okay, this is basically a label range that's saying depending on how many pseudo wires I create, I need 1 label for each of them. By default, it gives you a range of 10. But then the problem is if you go to add an 11th neighbor, there's not enough label space to do that. There's a command to say I want to add additional labels onto it. Okay, so these two happen to be used. They're numbers 49 and 50. And if we look at the other side as well, let's look at router 4 and show MPLS forwarding table. Number 31 happens to be the one that we associated as we advertise this over to router 2. Because it doesn't matter what the actual label number is, as long as it's a unique value between those two peers. So it's saying, I'm going to advertise to the route reflector that this is the range of labels that you can use. Then you're going to choose one, send me that traffic inbound, and I'm going to make sure that no one else is actually using that for the allocation. So it's part of the BGP negotiation between the two of them. Okay, there's another question here. In VPLS, do all types of traffic get transported transparently, like spanning trees, CDP, etc.? You can configure it to do that, but it does not do that by default. Where you configure this, I want to say it's under the VFI, which is going to be, if we show run section VFI, would be, now maybe it's under the bridge domain, because the bridge domain is actually the data plane. So let's say bridge domain 300. No, let's try into the VFI. The command is like L2 protocol something. VPN ID, what was it, 10? No, let me check the documentation. There is a way to do it though. This would be under, I want to say just under configuring virtual private LAN services. You must enable layer 2 protocol tunneling to run CDP, VTP. Okay, so how do you enable it? Layer 2 protocol tunneling. Let me just Google it. Cisco VPLS, layer 2 tunneling protocol. Actually, let me check the full guide because I don't know exactly where it is and what section it is. And I think if you just search for CDP, we should be able to find it. Oh, you know what? I think it's under the service instance. Let's try that at the port level. Show run interface gig 2. Gig 2 service instance 100 Ethernet. There it is, L2 protocol. Let's tunnel spanning tree. The routers are not actually running spanning tree on the other end. But this would be assuming you're attaching to a layer 2 switch, then yes, you would want to do that. There is also an option in the case that the customer is multiple attached to multiple PEs. And in that case, you need to extend spanning tree from the customer's network into the provider network, and then bridge spanning tree across to the other end. And the way that it does this is with multiple spanning tree. There's a much simpler solution to do this, though, is that on the customer edge, you don't put an Ethernet switch, you put a router, and then you run layer 3 routing like we are in this case in order to do ECMP between the multiple paths. But again, the reason why this is a potential problem is that the PE router becomes a transparent bridge, and if there's a loop in the network, then there's no way to break it because it's layer 2 bridging as opposed to layer 3 routing. Okay, so let's recap then this full config. And I am going to be adding these to the workbook a little bit later this week, so you guys will be able to take a look at the specific config and the show outputs for the verification for it. But you'll see they're pretty similar to each other in terms of their final config. Okay, so this is one of the PEs. We have the VFI, which in this case is doing BGP signaling. We have the bridge domain that is binding the VFI and the gig interface together. Okay, more specifically, it's binding the service instance on the Ethernet interface together. Then we have BGP that is doing peering to the layer 2 VPN neighbor. Okay, so again, important outputs for this, or the important portions of this config, is that we're saying we're discovering the neighbors through BGP. Once we have discovered the neighbors through BGP, we're going to advertise label values with BGP as well. So don't use LDP targeted sessions. In order to do that, though, we need to negotiate that capability in BGP exchange. So I'm not really 100% sure why they did not do it as two different AFI and SAFI address families, but the way they're mutually exclusive, where you either need to say this command is not there, which means VPLS is going to signal with LDP, or you can say that you're suppressing LDP, which means that VPLS is being signaled, the label value is being signaled with BGP. Okay, also, extended communities need to be there because without this, you cannot advertise the routes. We're then saying in the data plane, traffic comes in on gig 2, I don't care what the VLAN is, I'm putting that in service instance 100. Service instance 100 is part of a bridge domain that is 300. Okay, this is basically the virtual switch that we're creating. We're saying traffic as it comes in here, we're going to flood it out to all of the peers that are part of this virtual forwarding instance. In our case, these peers happen to be router 4 and router 5. Okay, they receive the traffic in the data plane in, they send it to their attachment circuit, so this is going to the customer edge routers. And then in addition to that, when the traffic gets flooded this way, router 4 and router 5 are learning the MAC addresses in the data plane. So it's the same as emulating a LAN switch, hence the name ELAN, as opposed to E-tree, which is going to be the next variation for HVPLS. But as compared to the previous case where we're signaling with LDP, the difference would be, and actually I'll post this text file as part of the initial configs there. This would be VPLS BGP Autodiscovery with BGP signaling. Okay, so it's kind of redundant. Then the other variation would be VPLS BGP Autodiscovery with LDP signaling. Okay, we say the signaling protocol is LDP. We don't need to define the VPLS endpoint ID. And we don't say this. Okay, the other key point is that this VE ID must be unique per PE. Okay, per PE within the within that individual VPLS. So the VPN identifier again is the route distinguisher. That's what's putting them into kind of like a VRF for layer 3 VPN. But within that, the VE ID is what's advertising the route. So if everyone shares the same route, then it's overlapping. It's like you advertising the 10 network, I'm advertising the 10 network. Neither of us are going to be able to use that, that particular information. Then final verification in the data plane from the PE router's point of view is to look at the show bridge group, or excuse me, show bridge domain. And then we should see that we're learning the MAC addresses out the pseudo wires to the remote peers, and then also that we're learning the MAC address to the local peers.